Okay, hello everyone, and thank you for joining my talk today on topological offsets. When you construct an offset around an object like this one, its topology is usually unknown because it depends on the offset distance. Here, for example, the offset will close the gap when choosing a larger offset distance. This behavior is desired in many applications like morphological operations that you can use to clean up noisy input data, so opening and closing operations. However, in many applications, you do not want to close the gap. And therefore, we develop topological offsets that are guaranteed to have the topology of an infinitesimal offset. Of course, this comes at a price. The offset distance then cannot be the distance in certain regions. We have to locally adapt the offset distance. Okay, I said that the topology of our offsets is guaranteed, but what is the topology of them? If you take all offsets with a distance very close to 0 and up to a certain threshold, you will realize that they all have the same topology. We call those the infinitesimal offsets. Only if you went beyond that threshold would the topology change. Our topological offsets are guaranteed to have the same topology as these infinitesimal offsets. Let me quickly introduce two related methods. The first one is actually my own work. Here we managed to construct offsets with sharp features and good mesh quality. The method was tested on Thingy 10K and proved to be very robust. However, we had a few cases with self-intersections in our output, and that bothered me quite a bit back then. The other method I want to mention is for constructing cages. It comes with topological guarantees that are very similar to ours. However, the input to this method must be a closed and manifold surface. And the output is a cage and not an offset. So while it is definitely related, the outputs of this method and ours cannot really be compared. So back to our topological offsets. For those, we know that we will not have any self-intersections, no intersections with the input, and that we have the topology of an infinitesimal offset. And these three things are guaranteed, not just experimentally, but we actually have proofs. And as you can see, some of them got quite lengthy, and it was a lot of effort to get them. So I invite you all to read them. It would be great if some of you would actually do that. The input to our method can be any simplicial complex. So it can have open boundaries and also non-manifold edges. And our proofs even support dangling edges and point clouds, so really any simplicial complex. The output of our method is a tetrahedral mesh. So you do not just get an offset surface, but you get a volume representing everything, the surfaces and the entire surrounding. Okay, how does this work? The first thing we need to do is embed the input in a volumetric mesh. In 2D, you can triangulate the domain. In 3D, there are methods like Tedwild or constrained Delaunay tetrahedralization. Our volumetric mesh has to fulfill specific criteria, and if it does, we call it a simplicial embedding of the input. Luckily, any volumetric mesh can be converted into a simplicial embedding with just a few simple operations that I will explain later. When we have our volumetric mesh, we can initialize a topological offset by simply performing matching TETs or in 2D matching triangles between the input vertices and any vertex that is not on the input. This surface is guaranteed to have the topology of an infinitesimal offset. And this is independent of the input geometry. So this is really a pure topological thing. It purely depends on the input topology. Finally, we can improve the geometry of our offsets with some remeshing. Here we do not allow any operations that would cause topological changes. Also, we don't allow for flipped volumetric elements because that way we can guarantee that there won't be any intersections of the offset with itself or the input. Of course, using a volumetric mesh also has some downsides. Most importantly, you have an increased runtime compared to methods that work purely on surfaces because we also have to remesh the volume. We tested our method on the Thingy 10K dataset, and to give you an idea, 55% of the inputs were, we created offsets within 6 minutes, but there were a few cases, more precisely about 3%, where it took more than 1 hour. So if the topology is really complex, it can take quite a while. Yeah, and that's our entire pipeline. And now I want to explain to you what the simplicial embedding is and how we can generate it. In a TET mesh, all TETs must be one of these 4 configurations to call the mesh a simplicial embedding. Here, the input is marked in blue. So every TET must either not contain any input, there must be 1 vertex on the input, 1 edge, or 1 triangle. And these are the only configurations that are allowed. If there are any other configurations, we need to modify the mesh locally to get rid of these configurations. And that is really simple. We just need a few splitting operations. If you have a TET where all faces are on the input, we split that TET into 4. If you have a triangle where all edges are on the input, but the triangle itself is not part of the input, then you split that triangle. And if you have an edge where the vertices are on the input, but the edge is not, you split that edge. So it's super simple, but it guarantees you to give you a simplicial embedding. And the advantage of the simplicial embedding gets clear when I show you an example, I guess. With simplicial embedding, we get the correct topology even in smaller structures like here with the fingers of the ogre. Without simplicial embedding, you might end up with topological issues, like the fingers are glued together here. Okay, so much about the simplicial embedding. I also want to talk a little bit about the offset optimization. I will not go into all the details, but I want to talk at least about the local offset distance that we are using. To avoid offsets from pushing against each other, we adapt the offset distance locally. We provide a heuristic so that the user only needs to specify a global target distance, and we then automatically adapt the distance wherever necessary. If we would not do that, then the offsets would start pushing against each other. And here in this 3D example, I think you can see it quite well. So the offsets never intersect, just to be clear. Even in that case, they never intersect, we guarantee that. But they will start to push against each other and get as floating point wise as close as possible. And if by adapting our offset distance locally, we can avoid that. So you don't really see the local part in that example, so let me show you another one. This rooster has some tunnels in between the feathers on its tail. And as you can see, the distance is just locally adapted. The local adaptation is here colored in red. And other areas like the head can reach the target distance without any issue. With just a tiny modification, our method is also capable of generating finite offsets, the classical offsets again. And these offsets are also self-intersection free and have no intersections with the input. So I could finally solve the problem that I had with my previous method. And even more, we can also generate multiple offset layers. This works for topological and also for finite offsets. And it is guaranteed that the offset layers do not intersect each other. Also, the output of our method is a tetrahedral mesh that contains all the offset layers. So it's one conforming mesh, and the layers are basically just tags in this tetrahedral mesh. And with that, I conclude my talk. I hope to see some of you at the poster later. Thank you very much.